right. So I keep saying long term, I said this multiple times in the earlier lectures also, but what really is long term, right. So we will try to quantify that now, right, by introducing the notion of something called return, right. So this is the common notation that I will use throughout, where capital T indicates the timestamp of the end of the episode, right. T means the end of the episode, right. Essentially I have reached S plus, right. So this is the most natural way of thinking about long term return, correct. This is the most natural way of thinking about long term return, and if that capital T is actually finite, right. So this is not a bad idea. I will sum up all the reward I am going to get in the future and I will try to optimize that, okay. So again you can see that if I try to optimize each one of these individually, what will happen? I might get a very high RT plus 1 and RT plus 2, but it might put me in such a bad ST plus 2. From then on, even if I behave optimally, individually for each of these numbers might be small, right. So what I really want to do is behave in such a way that even if some of these numbers are small, right, overall in the future the sum that I am going to get should be the maximum, right. So overall sum should be maximum. So that is essentially the goal that I have here, right. So this is fine, it works fine. There is one circumstance where this will not work, when T is, I mean there is no end, right. So I keep doing this forever. If I keep solving a problem forever, then it becomes a problem, and not necessarily forever. If I am also doing something over a very long horizon, if T is very large, not necessarily infinite, but T is very large also, I get into some issues, okay, because this will become a quantity with a large variance, right. So one other thing I should point out, this is something which people miss and get confused sometimes while reading on their own. So T here is a random variable, right. So every time I run the system, it might stop at a different time, right. Think of playing chess, right. There is a finite end point, chess will end, but every time I play the game I do not stop at the same number of moves, right. Even something like tic-tac-toe, right, even though there is an upper limit on the number of moves you can make, right, it is not necessary that you will always end up playing 5 moves, right. You might win in 4 moves, you might win in, well, yeah, if you win in 3 moves, well, okay, your opponent is really bad, but so you could win in 3 moves, you could win in 4 moves, or you could win in 5 moves, right, or you could not win at all, I mean, so you could still end up drawing the game. So like that. So T is a random variable. So when I put T here, it does not mean it always runs for some T steps, okay. So every time I run it, it will be a different value for T. So remember that, right, and consequently GT is also a random variable because all of these are random variables. I am talking about sums of random variables, okay, and a random number of those random variables are being summed up, okay. So GT is also a random variable that denotes the return, okay, great. So another notion of return that people typically use is right. In fact, I can even do that, okay. So go back and think about it purely from a mathematical perspective. So if my sum is going to run till infinity and my gamma is less than 1, and remember that individually each r is bounded, okay. So this sum will converge to something finite. So I do not have to worry about what I had in this case, this sum will not explode, okay. So that is fine, right. But there is even something more interesting about this discounted reward formulation. In fact, originally when people proposed the discounted reward formulation, it was not really from the boundedness point of view, it was more from a psychology point of view, immediate gratification versus delayed gratification, right. So if let us look at what happens if gamma is 0, everything will go, right, it is just RT plus 1. This goes back to just optimizing for the immediate payoff, right. So this gives you essentially you are going to behave in a way so that the next time step, what is the maximum reward that you are going to get. So you are going to behave only in that way, right. So if you think about what gamma is doing, so it is making, suppose I get a 10 here versus getting a 10 here, so 10 here is more valuable than 10 here, right, and of course 10 here is more valuable than 10 here, right. So let us go back to our robot grasping problem. We are talking about having a -1 all the time and then giving you 100 when you actually grasp. So instead of that I can say I am going to use a discounted rewards, my gamma is say 0.8. So what does it mean? So the sooner I grasp it, the larger the value I am going to see, correct. So the overall reward, I am starting from here, I should put myself in a trajectory so that I grasp this quickly, right, otherwise I will see some gamma power 10,000 into 100. So that is a very very small value. So the shorter I can get rid of the -1, right. So I do not really have to do the -1, but then what becomes tricky here? I have to figure out what is the right value of gamma, right. So that becomes tricky. So this is okay. So they use this kind of gamma to control for whether you are a nearsighted agent, only worried about immediate gratification, or whether you are okay delaying the gratification a little bit so that you get a higher payoff further down the line.
Why isn't there a discounted editor for bandits?
Yeah, only one payoff, right? So just pull.
I can cumulatively have, when I am doing the cumulative reward, I can give a gamma factor.
What, we don't do cumulative reward. So you are talking about regrets. You are talking about regrets, right?
Yeah.
When you are talking about the total reward case, right? So yeah, having a discount there really does not make sense, right? So anyway you are trying to optimize regret, right? So in some case your gamma is as small as possible, right? When you say you are optimizing regret, that means you are trying to keep your gamma as small as possible. So essentially you want all your winnings to come in one pool, right? And one pool I want to be optimal. So that is your optimal regret case, right? So when you are trying to achieve something like this, setting a gamma does not make sense, right? But I mean, if you can come up with a different objective function, maybe there is something that you can think of over the entire learning process, okay. So one thing which I should point out, just let me finish, one thing I should point out is that classically the RL people, right, look at bandit problems as immediate RL, right. I mean the learning, the whole interaction is just that one ampoule, okay, that is how we think of it, while the long term case is the full RL problem. But if you look at the people who work in the bandit theory community, right, they think of the interaction as the entire learning process, right. They do not think of it as one ampoule, they think of it as the whole process itself is the learning process. So for them it is like an episode, right. So it's a very different mindset. So the RL people don't think of it that way, and the bandit people don't think of discount factors and other things, because that is something which the RL guys came up with for looking at long term payoffs. So there is a mismatch of vocabulary there. So maybe there is something to find that in the middle ground, but I'm not sure.
Return is a function of the time step.
Return is a function of the time step, yeah.
Sort of. So we should try to maximize earlier returns rather than sort of later returns. As in which, how, what are the outcomes?
Let's put it this way. So I should optimize my policy in such a way that wherever I am, starting from there and going forward, I should get maximum possible return. So even if I am the last step, I don't want to goof up in the last step, right? If I'm, see, one thing you should remember is that if I know where I am going to end, if that capital T is given to me beforehand, then it becomes a non-stationary problem, because I will know, okay, I have 5 more steps to go, what should I do? I take 1 more step. I have only 4 more steps to go, what should I do? So immediately the problem changes, right? If I know the capital T, then it's a non-stationary setting, right? So we will not look at cases where the capital T is known. Okay, we will only look at cases where capital T is known to be finite, but not deterministic, right? It's not known a priori. So it's not like I can say that I will optimize only at the last step or anything, because I don't know what the last step is, right? I might recognize it when I actually reach it, but I don't know beforehand that, okay, I am going to have only so many steps to go. I mean, this is the normal setting that we assume, but you can immediately see it is not realistic, I mean, when you are playing chess, you can always say, hey, I am going to win in 3 more moves, or well, I am going to lose in 3 more moves, depending on, right, so how well the game is going. So in some cases you do have this kind of a little bit of a forecasting ability as to what the capital T is, but the basic setup that we will talk about will assume T is unknown. Yeah. So people understand why gamma equal to 1, I mean closer to 1 is far sighted, right, and closer to 0 is near sighted. Clear? Yeah.
In the second equation, aren't we a little biased to the action which is giving us faster reward?
What's that?
Like say I have 5 actions possible, and I picked an action which is giving me better reward in the first one. And there is another probability where I could pick another action first and then this action later, which is a higher reward in the longer run. But then in this equation we are actually giving more reward to the action which is done.
Well, depends on many things, right? Depends on the value of gamma and depends on the magnitude of the other rewards that you are getting, right? So let's say gamma is 0.99999999.
Then the bias is low.
When the bias is low, depending on how far sighted you want to be, you have to pick your gamma, right? So this is unsatisfactory. You have another free parameter, really free parameter that you have no way how to tune, but yeah, it's there, right? So we'll talk about another reward formulation shortly, which gets rid of the gamma but makes it very hard to optimize. Anyway, so any other questions on this? Doesn't matter, yeah, I just added up.
It will decrease the amount of reward we have.
Yeah, sure.
If an action should not be happen at all.
Yeah.
Like we gave some minus 100.
Yeah.
But if we multiply with 0.5 like or 0.25,
Yeah.
it will be like minus 25.
Yeah.
So we are reducing actually the reward point at the end.
But then that means I'm failing after more time steps, right? So I'm okay. I mean, whether it's positive or negative, it doesn't matter as far as these return definitions are concerned. You are essentially interested in maximizing the return. Therefore, if you are going to take an action that gives you a minus 100 reward, the farther out in the future you take it, it is better, right? So succeed for as long as you can and then die, right? So yeah, it doesn't matter. So the rewards can be positive, negative. Yeah, so reinforcement learning is this the community is little weird, right? So we talk about positive rewards and negative rewards, right? If you look at the psychology literature, they talk about rewards and punishments, right? For some reason the RL community, and if you look at the other places, they call it payoffs, right? Or they call it costs. Negative rewards are called costs, but in the RL community somehow thinks of negative things also as rewarding. So So we have positive rewards and we have negative rewards. But in the larger scheme of things, negative things also improve your experience. They enrich your life in some way. So you can think of negative rewards also. Anyway, so good. So this is fine. Then we'll move on to one more definition. I have to get this right. So what does that do? Just gives me the average, right? So the more the reward I accumulate, the larger the average is going to be, right? So for a finite number of n, this makes sense, right? But what if I have an infinite number of rewards in the future? Huh? Under mild regularity assumptions and boundedness of the individual R's, this will be bounded. Okay. What is not clear is that it will actually have a limit. It might not, right? In general, it might not have a limit. So you have to impose additional constraints on the kind of problems that you are solving. Not all problems have this defined, right? Or you can make some small variations to this to make sure that all problems have this limit defined. Okay. So there are slight different, the limit can be, you can play around with the limit. For example, one case where limit will not exist is this, if the sequence is periodic. Right, if the sequence is periodic, then the limit won't exist, right, because it will just keep oscillating all the time, right. So in this case we use something called the, people know how to handle limits of periodic sequences? Use something called the Cesaro's limit, which essentially looks at the average over periods and lets the number of periods run to infinity, right. So in the reason the limit does not exist is because you cut the sequence in the middle of a period, right. So if it is going to be periodic, so you only take a period as a unit and take the reward over the period, right, and then you keep adding that over subsequent periods and take the average, right. And limit as the number of such periods you consider goes to infinity is called the Cesaro's limit. Then in such cases limit might exist, right. And of course there are a bunch of other conditions you have to put on the actual structure of the problem itself for you to ensure that this limit exists, but for a very broad class of problems you can talk about these limits as well. So the nice thing about this kind of the return definition is that it does not have a pesky gamma parameter, right. So it makes it nice from a computational point of view not to have the gamma parameter, but it makes it little weaker from one of the original motivations of RL point of view, because it does not have the gamma parameter. Okay, so gamma parameter allows you to have some sense personality for your agent, right. Is it a near sighted agent or a far sighted agent and so on and so forth, right. So especially people in neuroscience, when they are looking at modeling reinforcement learning humans, right. So they actually have, they can think of estimating what is your gamma by running experiments with you, right, because it's kind of it's a personality issue thing, right. So some people will tend to be, in fact there are studies that try to correlate the levels of serotonin in your head to gamma, right. So more the serotonin, the larger the gamma value you have in your decision making and so on and so forth. I mean, it's like, it's really weird how we seem to have all these parameters in our head tied up with different kinds of neurotransmitters, right. Anyway, so this is called the average reward. This is called average reward return. So any guesses what this is called? discounted return that sorry I can't hear cumulative or total return or right. So people, yeah, if you're going to call that cumulative, then you have to call this cumulative discounted return. Okay, so there is a very nice problem that people use for motivating why discounted return is bad. Okay, so let me try and do that here. Okay. So I am implying no theological leanings here. Okay, this is just a fun example. So that's earth. Okay, that's heaven, and that's hell. So the path to heaven has a minus 100 reward, and the path to hell has a plus 1000 reward, right? But once you reach heaven, you get a plus 1 infinitely. Once you reach hell, you get a minus 1 infinitely. Huh?
You get a chance to go back?
I said I'm not getting into theology here. Okay, this is just a fun example. But of course, you can always think about other things. Yeah. No reward for? Nah. Anyway, you are finished here, right? It's a transient state. We don't care. But then, if I set gamma is 0.1 or something, right? You will prefer going to hell. Right? If gamma is like 0.9, in fact, gamma has to be pretty high for you to go to heaven. Right, so it's the same problem. So now gamma becomes part of the problem definition, right? Depending on what value I set for gamma, my optimal policy itself will change, right? So this is not a desirable state of affairs. I mean, if you are thinking about saying, okay, here is a problem, solve it, and it turns out that if I use average reward scenario, which is better? Going to heaven is better always. Doesn't depend on anything. What does it depend on? I am going to get an infinite number of plus ones, right? That will pulp any my negative things I get initially. I am getting a finite value for negative here. I am going to get a minus infinity there and a plus infinity here. So that trumps anything that happens here. So average reward will tell me that this is the best thing to do. But if I am going to use discounted returns, so I will go up or down depending on what my gamma is, right. So now you can immediately see that discounted return is a more realistic return because not everybody is going to heaven, right. Anyway, that is the fun part. We'll come to the really one of the crux of reinforcement learning here, right, and the full RL and a lot of the algorithms that we will look at, the notion of a value function. But we already looked at a value function, right, but the value function we looked at was very simplistic, right. So what did we do there? We said, okay, average of all the rewards I obtained so far, right, that is the value function. Then we had another value which we looked at, which is the true expected reward that I should get if I take an action, right. So we denoted that by Q star, and then we denoted by Q the average that I am maintaining for this, right. But here we have something more complex, what do we have here? We have a policy pi which determines not just the current reward but also the sequence that I am going to see henceforth, right. So, when I am going to talk about a value function here, I will talk about something called V of pi, right. So, V pi is the value function associated with a policy pi, right. So, when I say V pi of S, so this is essentially the expectation of, so what should I be taking the expectation of? Rewards or returns? What do you think I should be taking the expectation of the returns, right, because the return is what I am looking to optimize, this is what I should be predicting. So, in the bandit case I was only looking at the reward, so I was just making out as the expectation of the reward, and here I should make it out as the expectation of return. So, given anything? Anything else? I need to condition it on pi, right, because I already have a pi here. So why do I need to condition it on pi? Because my GT is going to depend on pi, regardless of what formulation I am using. The subsequent rewards I am going to get depend on the actions I take, right. So, I really need to know what my pi is, right. So, I need to condition it on pi. So, we will denote it like this, right. When I write the pi here, that means that is the policy I am conditioning on, okay. The expectation with respect to the distribution generated by following pi, okay, of GT, given that at time t I started with state S. Okay, does it make sense? Everyone on board? Right. So, I am starting from state S, I am following pi, I am generating one trajectory, right, like this, right. So, I start from S, okay, go to some S prime, go to S double prime, so on, right. So, every time I take an action, so I will take A prime, A double prime and so on, and I will get some R. Right, this is one trajectory. So, like that I will start from S, I will do another trajectory, then I will start from S, I will do another trajectory, I will start from S, I will do another trajectory, then I will be getting all these rewards, like I have R prime, R double prime, like that I will get some R1 prime, R1 double prime and so on and so forth. Each trajectory I will get one such sequence of rewards, right. So, I will add up all of these, or I will take a discounted sum of all of this, right. So, I will do that, right, and I will take the average. So, that is essentially whatever that average will converge to is my expected value for this. So, this is essentially what I mean when I say GT such that ST equal to S, that means I will start with S, okay, and compute this rewards, okay. Right. So, is it clear why we need to condition on the pi as well, right, the future is going to depend on pi. Yeah, I am talking about the expectation here, I am just explaining to you what the expectation is. So, every time I generate a trajectory through pi, right, two things could happen. A, I could pick different actions because pi is stochastic. B, the world could change in a different way because the world is stochastic. So, in the same S I could take the same A, I might end up in a different S prime every time, right. So, there are multiple ways in which this stochasticity can operate. So, one, pi itself is stochastic, therefore, in the same S I need not take the same action again, say first time I can take A1, next time I can take A2 and so on and so forth, right. That will completely change the trajectory that will come later, or I will take the same A, right, I might end up in a different S prime because of the transition probability. So, every time I do this trajectory I will get some different trajectory, I mean every time I generate a trajectory I will get a different sequence, right, and the expectation is over all such sequences, Okay, what is the total reward I will get? So that is essentially what the value function is. Okay, is it clear? Great. Let's confuse people some more. So we had Q earlier, right? So what was Q of A? Q star of A was the true thing. Q of A is the expectation, your expected estimate for taking action A, right? But then here we have to worry about taking action A in a specific state, because every state it is going to be different. Correct? Every state it will be different. So what this will be? I still have to do this. I still have to do this. So what is the big difference between the V and Q? Sorry? Yeah, action A is fixed. So earlier when you were generating trajectories for V pi, I said you start with S, right? Then you go to S prime, then you go to S double prime and so on and so forth, and then you could, I said you could pick any action. So first time you will pick A, then A prime, so next time we will put some A1, so like this, right? So you could pick different actions every time you generated the trajectory. So now I am saying you can't do that, right? So every time you generate the trajectory you have to pick A first, right? But subsequently you pick actions according to pi, right? The first action is something that is fixed now. The first action will be A all the time. So what does this tell you? It tells you how good is it to perform action A in a given state. So earlier you did not have that information, but now you have the information about how good is it to perform action A in a given state. Okay. Is it clear? Going back and thinking about the problem itself, right? So there is a problem that we are trying to solve, right? So how do you define the problem? How do you characterize the problem, right? So I am in a state S, I take an action, okay, I go to a next state and I also get a reward, right? So for me to characterize the problem, I need to tell you how this transitions happen and how the reward generation happens, right? So I need to really look at this following question: what is the probability of given sorry not RT plus 1 given, is that sufficient? I mean, think about it, right? Riding a bicycle, so you probably need to know what is the velocity, momentum that you had before. I mean, it's not enough to know where you are on the road and how you are tilting. You might want to know something more about the history of how you got there, right? Right? So you really need that quantity. Okay. So you need to know what is the probability of ST plus 1 RT plus 1 given everything that went before that. Correct? Now this becomes a little complex to model because the number of parameters you will need for modeling something like this becomes pretty pretty huge, right. So, what we typically end up doing is make a very strong assumption that this guy is equal to see what you truly need is the first quantity, right, because that becomes very hard to estimate, very hard to define. You make the assumption that that quantity is really equal to this, right. So, what is this assumption called typically? Markov assumption. It is essentially a first order Markov assumption where the history does not matter, right, only the current state and current action matters, that will determine what the next state and next action will be, right. So, we make a further assumption which is what is the assumption I made? Stationarity, right. So, we will typically operate in Markov environments, right, and we will typically assume they are stationary. Okay. So, for me to characterize the problem, now what should I give you? What I need is, what is the question? Yeah, to specify the problem, what are the things I should give you? Okay, I should give you the states over which the problem is defined, right. I need to do that, right. I need to define the state space over which the problem is defined, and then the set of actions that I can take, and right, the P function, right. So, I need all of this to define the problem completely. Anything else I need? Depends on what is the return I am using. I might also need a gamma, right. If my return, if I am using a discounted return, depending on what the value of gamma is, the problem changes, right. That is what we discussed. So, if I am going to use discounted return, I should also specify gamma as part of the problem. Okay. So, is it clear? So, I need all of this to define my problem, right. In some cases, we use a slightly simplified definition where instead of having the single joint distribution S over S prime and R, right, we also give it as two separate quantities. So, I will suggest S, I mean I have to specify S A, then I will specify that. So, what is that called? Sometimes called the transition function or transition probabilities, okay, and then I will specify the expected value of the return given that at t I was in S, I did action A and I went to S prime, right. So, essentially I am writing this out, splitting this up, right. So, instead of giving my joint distribution, I am saying okay, no, I will specify the S prime separately, and for the R I will condition it on S prime also, right. So, you can think of some sense I am using the chain rule and splitting the joint probability as P of S prime into P of R given S A S prime, but what is the difference here? Instead of specifying P of R given S A S prime, I am giving you only the first moment, first moment or 0th moment, I mean the first moment of the distribution, right. So, why is this enough? Why is this enough? Because I am going to be optimizing only the expected value of GT, right, and GT is composed of these guys, right. So, essentially I will be taking the individual expectations of each one of these, right, and that is enough for me. I do not really need to know the distribution which generated these rewards, because individually I will be taking the expectations of each one of these rewards, and therefore knowing the expectation alone is enough. So, sometimes you specify the problem like this, right, and this is typically how you would specify what is called a Markov decision process. So, it is a system, it is a decision system that you have to, for every state you have to actually keep giving a decision, right, and it follows Markovian dynamics, right. Both the transition and the rewards follow satisfy the Markov property, right. So, such a system is called a Markov decision process, right. So, you have states, you have set of decisions, right, and the evolution of the states follows the Markov process, okay. So, they are called Markov decision processes, okay, and what we will assume is that the reinforcement learning problems that we are trying to solve can be modeled as MDPs. Okay. We will assume that the reinforcement learning problems we are trying to solve can be modeled as MDPs. So, in some sense a value function really is useful only if you have the Markov property. Why? Because I am assigning a value to a state regardless of how I got to the state, right. So, if the Markov property is not satisfied, how I got to the state will influence what happens in the future, right. Since I am saying that I do not care about what happened in the past, I am just saying I am starting in state S, okay, and I am going to be following policy pi hereafter, what is the expected return. Therefore, I am saying history is irrelevant, right, when I am defining a value function. Another way of thinking about it is, here the value function is marginalizing over history. So, it is essentially taking the expectation regardless of what the history was. That is one way of looking at it. I mean, in some cases that is how you make sense out of the value functions, because as we go along later we will see that we actually apply RL blindly to problems that are non-Markov, right, and we will be using the V function and the Q function in such cases. So, the only way to make sense out of what is happening in such cases is to say that, hey, we are essentially marginalizing the history. So, we are just doing taking the expectation over all possible histories as well. It may or may not be a sensible quantity, but if it works, hey, you just use it, right. But normally the value function makes sense only if you have the Markov property. Forget about the future, right, and because you are ignoring the past, it makes sense only if you have the Markov property, right. Does it make sense? Right. So, that is why I was saying that I should have probably defined value functions after telling you about Markov decision processes, but it is okay, you can still understand it in the general sense as well. Great. So, the next thing we have to talk about is optimal value functions, right, but I will start that in the next class.